All right, welcome back. Today, we're not just solving a problem, we are opening a case file. I want you to picture a dimly lit office, an evidence board sprawling with connections, and a single sorted list of numbers that holds a secret. Our job? To crack it. The file's open. Let's dig in. This right here, this is the philosophy that's going to guide our entire investigation. It's the core of our whole approach. We're not just randomly looking for a needle in a haystack. No, we're using the very structure of the haystack to lead us directly to that needle. This is all about pure deduction. Okay, so every good investigation starts with a case file, right? And ours, well, it looks deceptively simple. But don't let that fool you. It contains every single clue we need. The real challenge isn't just about finding the answer. It's about finding it in the most elegant and efficient way possible, using every piece of evidence we're given. So here it is, the heart of the matter. We've got a list of numbers, all neatly arranged from smallest to largest, and we've got a target value. We know that somewhere in that list, there are two numbers that, when you add them together, equal that exact target. Our job? Find them. Now, before we jump in and make any moves, we have to do what any good detective does. Analyze the crime scene. In our world, we call that the problem space. This is where we figure out the rules of the game, the environmental factors, and most importantly, the critical clues that are going to shape our whole strategy. So what's our crime scene look like? Well, first off, our input is a sorted array of integers. What that means is every single number in there is a potential candidate. And this is the key part. It's not just some random jumble of numbers. It's an indexed, ordered sequence. And that structure is everything. And this, right here, this is the smoking gun. This is the single most important clue in the entire case file. The fact that this array is sorted isn't just some minor detail. Oh no, it's an incredibly powerful constraint, one that we can and absolutely will exploit. It creates a relationship between every number on that list. So what does that sorted order actually get us? Well, it gives us this incredible power of what's called directional elimination. Think about it. If you pick any number in that array, you instantly know that everything to its left is smaller, and everything to its right is bigger. This lets us make smart, decisive moves instead of just guessing all over the place. And our last big clue is actually a restriction, a rule we have to follow. We have to solve this case without using any kind of external recorder. In programming terms, that means constant extra memory. We can't just write down a bunch of notes or build a separate list of suspects. We have to solve this with only what's right there in front of us. In every investigation, there's always that one core truth that has to be satisfied. We call it the invariant. And for us, it's this simple little equation you see here. Candidate 1 plus candidate 2 must equal our target. It's the law. Every single move we make from here on out has to be to satisfy this one truth. Okay, so we've got the lay of the land, we understand the case. Now it's time to bring in the usual suspects, our potential methods for solving this thing. We're going to line them up, interrogate each one, and see which one can actually get the job done within the strict rules we've uncovered. So the question we've got to ask each of these methods is pretty simple. Can you solve this case while respecting all the clues we found? The sorted order, the need for top-notch efficiency, and that absolute ban on extra memory. Let the interrogation begin. First up, we've got the brute force nested loop. It's thorough, sure. It compares every number to every other number, but it's way, way too slow for our needs. Rejected. Next in line, the hash map. It's fast, yeah, but it builds a whole separate list of suspects on the side, and that violates our no external recorder rule. So, rejected. And that leaves us with one prime suspect, the two-pointers method. It's efficient, and it uses zero extra memory because it masterfully uses the sorted nature of the array. It's the only one that respects all the clues. We've got our method. All right, we've picked our method. Now it's time to prove it. We're going to walk through the deduction step by step. And you'll see how the two-pointer method doesn't really search for an answer, it closes in on it by systematically getting rid of everything that isn't the answer. Okay, so here's how this brilliant method works. We place one pointer at the very beginning of the array, on the smallest number, and another pointer at the very end, on the largest number. Then we check their sum. If that sum is too big, well, we obviously need a smaller number, so we move the right pointer in one step. If the sum is too small, we need a bigger one, so we move the left pointer in. It's this beautiful, logical pincer movement that just closes in on the solution. Okay, let's put this to the test with some actual numbers. Our array is 2, 7, 11, 15, and the target we need to hit is 9. Time to deploy the pointers and see this deduction in action. Okay, first move. Our left pointer's at the start on the number 2. The right pointer is at the end on 15. We add them up. 2 plus 15 is 17. Our target is 9, so 17 is obviously too large. And the logic here is just undeniable. To get a smaller sum, we have to get rid of the biggest number. So the right pointer moves one step to the left. And just like that, look what happens. The left pointer hasn't moved, it's still on 2, but the right pointer has now moved over to 7. We calculate the new sum. 2 plus 7 is 9, and that is a perfect match for our target. Our invariant is satisfied, the case is solved. And this is the really cool part, the key takeaway. The algorithm didn't just stumble upon the answer, it never guessed. At every single step, it made a pure, logical deduction based on the sorted order of the numbers, eliminating all the possibilities until the only thing left was the correct one. It was simply verifying the truth that we already knew had to exist. All right, the solution is in hand, our method is proven. It's time to close this case and file the report. The final verdict is going to be based on just how efficient our chosen method was. So first up, the time report. Because our 2 pointers just start at the ends and move toward each other, we only make one single pass through the array, at most. This means the time it takes is directly proportional to how big the array is. That's what we call linear time, or O of n. Incredibly efficient. And what about the resources used? Remember that clue? No external recorder? We only used a couple of pointers to keep track of where we were. That's it. That's called constant space, or O of 1. It means the memory we use doesn't change, no matter how huge the array gets. Just a perfectly clean operation. We left no trace. And that really brings us to the big idea here, our final conclusion. The solution wasn't really found when we ran our little test. It was guaranteed from the very beginning, the moment we analyzed all the constraints and chose the one and only method that could honor all of them. The execution was just a formality. The real detective work was the deduction we did beforehand. So this leaves us with one last question to chew on. If the answer is basically predetermined by the constraints of the problem itself, then maybe our goal isn't just to find an answer. Maybe what we're really searching for is that beautiful underlying logic that makes the answer inevitable in the first place. Case closed.